where we left off, I just introduced to you this new concept of isoelectronic, and it helps you think about the tendency or driving force for things to become more stable. When an element is close to its position to a noble gas, the tendency will be to gain or lose electrons to be more stable. And more stable, now you're starting to learn, means that the valence shell, whatever it is, right? And you should know what the definition of a valence shell is now. It's full. If the valence shell is full, that's going to be the stablest configuration for electrons that have about that number. Okay, about that number means, like for this example, with sodium was one more than neon. So it has one more electron than neon has. And as you're discovering now, that one electron is in the next higher energy level. So by putting that electron in the n=3 level, now our valence shell has one electron. But if it lost that electron, if it could, it would become isoelectronic with neon and be more stable because it now has the stable electron configuration of a noble gas. The same is true with fluorine that I have at the very, very top. Fluorine is one away from that configuration. It's lacking that one electron. If it can get it in a chemical reaction, the tendency will be for it to gain that electron, because in doing so, it becomes more stable. And stability is the overall driving force for these reactions. Now, when we say isoelectronic, the examples I'm showing you here, for example, sodium plus, the sodium plus ion is isoelectronic with neon, but this is an ion, okay? The ion is isoelectronic with the neon atom, but the electron configuration is the same. They both are 1s2, 2s2, 2p6. So if I just gave you 1s2, 2s2, 2p6, you wouldn't necessarily know what it was representing. I would have to tell you more information, like this is an ion or it's an atom. If I tell you that that's an atom, then you know that there's only one thing it could be. All right, if it's an atom, that electron configuration is the neon atom. It's the noble gas. But if I tell you it's an ion, it could be a number of things. As an ion, it could be the sodium ion. The fluoride ion would also be isoelectronic. What do you think the trend would be? Extend it beyond just gaining and losing one electron. Oxygen. All right. Oxygen is 2 away. Okay. So if oxygen were to gain 2 electrons, what would the charge on that ion be? 2 what? Plus or minus? 2 minus. That's right. And as you'll learn later on, that's called the oxide ion. What if we go one more? What about, what's after sodium? What's that element, Mg? Magnesium. Would magnesium do the same thing? Yeah, it would. How many electrons does magnesium have in its valence shell? It has 2. All right, it's 2 more than what we have in the nearest noble gas. So it's going to lose those 2 electrons because the driving force is that if it can lose them, it will become isoelectronic with its nearest noble gas. In this case, it's going to lose 2. So it's going to be a 2. Now it's going to be a positive charge. But all of these ions are isoelectronic with the electron configuration of the nearest noble gas, which is that of the neon atom. Okay? And they all look like this: 1s2, 2s2, 2p6. All right, I can show you the same example with argon. The example I showed you last time was with the chloride ion. Now we've got, it's the same thing, except now we're finishing out the n=3 valence shell. The chloride ion, sorry, the argon atom has this configuration. You can see why we like using the shorthand. It would be the neon core down here. So everything that we have in neon, and then we just show the valence electrons, 3s2, 3p6. That's the argon atom, but all of these ions would be isoelectronic with it, all of them. I'm just showing you one right now, the chloride ion. What else would be isoelectronic with the argon atom? Potassium. Where's potassium? Potassium is one more than argon. What's the symbol for potassium? It's a K. So what would the charge be on the potassium ion that would be isoelectronic? 1 plus. So we don't put the 1. If there's a 1, we don't put it. Okay, it's just a plus. What if we go 2 more beyond argon? What do we have? A Ca. Calcium. Calcium 2 plus. What if we're more than 1 below argon? What's S? What's capital S? Sulfur. What's the charge on sulfur? It's 2 minus. Okay, we can even go beyond that. We can go phosphorus and become the phosphide ion, 3 minus. Yes, question. So the question is, potassium and calcium, would they have the same electron configuration as argon? No. As a neutral atom, they wouldn't. But if they lost or gained electrons to become more stable, the ions would be. So I need to clarify that. So the potassium ion, the K plus, right, that is isoelectronic. But potassium by itself, if we were to do the neutral, but the neutral potassium isn't going to be isoelectronic. So this brings us back to the end of our discussion of quantum theory, where we learned about the solutions to the Schrodinger wave equation, and we had all these sublevels, the S and the P and the D and whatnot, and it looks confusing, but the periodic table is arranged so that, well, it's arranged based on the quantum theory of where the electrons are placed in their energy levels. So if we continue along with this, here, let's go back to sodium, which is the example that we were talking about before. So sodium, if we fill it in from the beginning, we have the 1s sublevel, and that's got its 2 electrons, and we can see where they are now on the periodic table. The first one would be here, the second one would be here. If we stopped there, if we just had 1s2, we would be describing the electron configuration of helium. If we go to the next element, 1 more proton, 1 more electron, that's lithium. That's going to give us, now those electrons go in the 2s level, and the electron for lithium and the electron for beryllium both go into the 2s sublevel. If I were to stop there, that's the most energetic electron. We're doing the Aufbau principle. Remember that, Aufbau, filling up from the lowest energy level to the highest. So if we stop at beryllium, the last most energetic electron we place is at 2s. And that's where beryllium is found in on the periodic table, in the S block over here. But if we were to continue along for boron, carbon, nitrogen, oxygen, here, let's stop at oxygen. So that would be 2p. We're adding 1, 2, 3, 4 more electrons. So that would be 2p4. If I were to stop there, the most energetic electron I've added is to the 2p sublevel. So I would expect that element that we're describing to be found in the P block, which is on the right-hand side. Right? So you can read all this stuff off the periodic table. If we go all the way to neon, though, this would be 2p6. And now we're full. Then to get to sodium, we need to go 1 more. That's going to be at 3s1. All right, so this is just review. We've done sodium plenty of times. And now we've been talking about when sodium atom, okay, if it loses this electron to become more stable, that's going to then turn into the sodium ion, which would be described as 1s2, 2s2, 2p6. That's isoelectronic with its nearest noble gas, the atom. Okay, so this is the sodium ion, but it's isoelectronic with neon. All right, so the trend that I want you to pick up on now is that if we were to do this for potassium, and we did on the previous slide, potassium also has 1 valence electron. So it's going to lose that 1 electron to become more stable. And we have the sodium ion will do this, the potassium ion does this as well, and it will lose 1 and become a 1+ charge. What about Rb, rubidium? How many electrons are in the valence shell of rubidium? There's 1, right? This is all of these periodic trends, just like we studied in chapter 2. Rubidium would do the same thing. Rb, it has 1 valence electron, so if it can, in a chemical reaction, its tendency is going to be to lose that 1 electron to become isoelectronic with its nearest noble gas. Now, what's the nearest noble gas to rubidium? It's krypton, it's Kr, sorry. Okay, so when you're trying to find the nearest noble gas, it might be backwards from the element that you're trying to decide, is it going to gain or lose electrons? But you already know this trend from chapter 2. The metals are going to lose electrons to become positively charged cations. Okay, so everything on the left-hand side here, whether it's in the S block or if it's the transition metals, they're going to lose electrons. Now, the trend I want you to focus on, though, is you can read this right off the periodic table. In fact, look at the number that's written on the top of the column. We have a 1 written up here and a 2 written up here. Okay, that's also telling you the number of valence electrons that are in any element that's found in those rows. Okay, and from that you can deduce what the charge would be if it gained or lost electrons. So metals are always going to lose electrons. So anything that's in group 1, lithium, sodium, potassium, rubidium, cesium, francium, they'll lose, their tendency is to lose 1 electron and become a 1+ positively charged cation. Anything in group 2, beryllium, magnesium, calcium, strontium, barium, right? Those are going to lose 2 electrons if they can to become more stable. You can see that on here as well, all right? You've got a 1, you've got a 2. Sometimes it's also listed as 1A, 2A. Sometimes you'll see them with Roman numerals, but you can still read them off the periodic table, the number of valence electrons. If you look on the right-hand side, you've got 3A, 4A, 5A, 6A, 7A, and 8A. And you also have them written as 13, 14, 15, 16, and 17, and 18, okay? You can still read the number of valence electrons from those. This one just has 13, 14, 15, and 16. But if you look at the second number, 3, 4, 5, 6, 7, 8, that also tells you the number of valence electrons. So if you work towards this idea of 8 is the maximum that you can have, and you're stable if you have 8. So the driving force is to get to 8. Now I'm skipping the transition metals for now. Let's just look at the main group elements, the ones that are in the tall columns here. There we can count 1, 2, 3, 4, 5, 6, 7, 8. Okay. If you're a metal, you're going to lose the electrons, and you can read what the valence number is, the number of valence electrons that it has in the valence shell. Okay. And you can deduce what the charge state would be. So boron, for example, or let's go to aluminum instead. If I were to give you an atom of aluminum and ask you, is it going to gain or lose electrons to become most stable with the nearest noble gas? Let's just see a show of hands. We don't need the ABC cards for this. How many think aluminum will gain electrons to become more stable? Gain electrons. How many think aluminum will lose electrons? Yes, it will lose. Now it's a little deceptive here because aluminum is on the right-hand side of the periodic table. But it's how close it is to the nearest noble gas. If aluminum were to gain electrons, it would have to gain 1, 2, 3, 4, 5 electrons to become isoelectronic with argon. But it only has to lose 3 electrons to become isoelectronic with what? Neon. Okay. So aluminum, if it can, it will lose electrons and become a 3+ cation. Just also think of it as metals. Metals will always lose electrons. Now, I don't have the metalloid shown on this one. Now, it's a little trickier when you're working with things that are in group 15, 16, and 17, because they're going to gain electrons, but how many are they going to gain? For example, we already did phosphorus. So let's take a look at phosphorus. Phosphorus is going to gain electrons. How many electrons is it going to gain? 3. Now, you know that because you're working towards a noble gas. But the valence, how many valence electrons does phosphorus have in its valence shell? It has 5. And you can read that right here in the 5 of the 15, or in other periodic tables, it will have a Roman numeral 5 there, or may say 5A. The A, by the way, just stands for it's the main group elements. You'll have a B if it's a transition metal or an intertransition metal. Okay, so as long as you're working with this idea of H, you can deduce exactly what these ion charges will be if they can gain or lose electrons. That's why with oxygen, right now you can read oxygen. You don't have to remember that oxygen would form a 2-. You can read it right off the periodic table. How many valence electrons does oxygen have? It has 6, so it only needs 2 more to get it to its most stable configuration, that being the nearest noble gas. Now, the transition metals are different. You can't predict for the transition metals what the charge state will be. A lot of the transition metals can have more than one charge, depending. Like, for example, iron, you can have iron as a 2+, or you can have iron as a 3+ ion. Copper can be a 1+ or a 2+, right? So you can't necessarily predict just from looking at its position on the periodic table what the charge state of the ion will be if it's a transition metal. But you can if it's a main group element. All right, so let's practice a little bit. You don't have slides on this, but let's consider these as clicker questions now. You have your ABC cards. Here's an electron configuration, and not the ion. Which atom does that electron configuration represent? Beryllium, neon, or carbon? And, well, here, I won't say and yet. Think about it. All right, raise your cards up real high. Let's see what we got. I see C. Most everyone has got a C up. Let's see. Is C the right answer? Carbon. 1, 2, 3, 4, 5, 6. Yes, it's carbon. How many valence electrons are there? Just 4. Okay. And you can count the boxes then, and N equals 2. 1, 2, 3, 4 brings us over here to carbon. Notice that I'm using the written words for the elements. Remember, I told you I wanted you to memorize and know the symbols and the names for everything up to, what did I tell you, xenon, I think? All right, how about the orbital diagrams? I didn't talk about those yet today, but let's remember now, how would we represent that electron configuration as an orbital diagram following Hund's rule and how we fill electrons in the orbital diagram? Okay, you see mostly the right answer. It's A, it's not C. Now the only difference between A and C is that in C, I have the electrons shown as an opposite spin. Now that's a real subtle difference, okay? But when you have unpaired electrons in separate orbitals, it's slightly more energetically favorable, so lower energy to keep them stable, if all of the magnetic spins are aligned. All right, good. Let's do some more. Again, for the atom, which atom is described by that electron configuration? B, sulfur. We can see the number of valence electrons. That's the total number of electrons that are in the highest energy level that has electrons. 6 valence electrons, you can go to group 6 or 16, and any element that's in that group should have an electron configuration that when you get to the valence electrons, it's S with 2 in it and P with 4 electrons in it. Whether we're at the 3 level, the 4 level, the 5 level, it doesn't matter. Very good. Now here's the abbreviated form of that same configuration. Instead of writing it all out, now I'm just showing you the shorthand. So it's everything that's in the neon core, and then we're just focusing on the valence electrons. So again, following Hund's rule, what's the right orbital diagram for this? All right, yeah, C seems to be the consensus, and that's correct. It's C. Remember, in Hund's rule, all of these orbitals, we start with them being singularly filled. Each orbital has 1 unpaired electron in it before you have both electrons paired. Even though I told you earlier that it's more stable to have them paired up. Yes, that's true. But Hund's rule overrides that because it's still more stable yet to have 1 negative charge in each of the 3 areas, because those areas are non-overlapping, okay? but they all specify the same energy level. So it requires more energy to keep both of those negative charges confined to only 1/3 of the space. Good. Let's see, what else do we have here? What atom does that configuration describe? It's argon, right? Because we're full with argon. So if we go one beyond argon, what's the electron configuration for the element that's one beyond argon? What is the element that's one beyond argon? It's potassium. B, let's see. B is the right answer. But why isn't it A? Why is it B and not A? Go ahead. That's true. Okay, so this student noticed that potassium is in period 4. So those electrons in the S block have to be at n equals 4. That's good. Yeah. Okay, so he said that it's shown here in A that the next electron goes in the D sublevel, but you have to go to S first, right? But what about the fact that yes, that's true, but this is a 4. We know that at n equals 3, if you go back to solving the Schrodinger equation wave functions, okay? And if you look at those rules at n equals 3, here, let me remind you of some of these here. At n equals 1, we have one sublevel, L equals 0, that's the S sublevel. There's only one orbital. When n equals 2, we have two sublevels, S and P. When n equals 3, we have three sublevels, S, P, and D. And I was telling you that we fill things up before you move to the next level. 4 is the next level above 3. Okay, so there's still 3D to be filled. So why are we filling 4S first and not 3D? Yeah. 3D is a little higher energy level than 4S. That is the right answer, all right? But that's just something that you learn, unless somebody showed you more in depth why that's the case. I'm going to try to show you a little more in depth now why that's the case. But B is the right answer here. And this is the first departure to the so-called rules that you were learning by just increasing the energy level by following the quantum numbers, 1, 2, 3, 4. And then within a principal energy level, we fill S, and then we fill P, and then we fill D, and so on and so forth. All right, this is a little unique. And you can tell that from the periodic table. Always trust the periodic table because it is organized based on how we actually observe things in nature and as it follows quantum theory. So this is telling us right here that 4S fills before 3D. And the explanation for that in words is that 3D is a slightly higher energy level than 4S. But that's just a statement. I haven't given you any evidence for that. That's just what you learn. If you accept that as a true statement, however, then we are still following the Aufbau principle, right? This follows the Aufbau principle. We're still filling in our electrons in increasing order of energy level. All right, so I'm going to try to give you a simple explanation of why that may be, but it has to do with getting a little bit more complex. Remember, we don't know where an electron can be found, but within an orbital, remember, an orbital is described as a square of the wave function. And it's a theoretical distribution. Or let's not say theoretical, it's a probability. Probability of where an electron can be found. And the other thing to remember, when things are stable, we've got positive charged in the nucleus and we have negative charges on the electrons. So when those negatively charged electrons, if they can get closer to the positive charge of the nucleus, they're more stable. There's more of an interaction there, stabilizing force. Okay. So that's something else to keep in mind. Electrons closer to the nucleus these are more stable. And if you're more stable, that means it's the same as being in a lower energy level. The energy levels are just the amount of energy necessary to keep things stable. Okay. So the closer the electron is to the nucleus, the more stable it becomes, and that gives us a lower energy level. Now, in the upper left-hand corner here is shown kind of this probability. If you were to take the square of the waveform and kind of map out its theoretical distribution, you would find something like this. It's not just, and this is just a quarter of a sphere. So imagine that this is a three-dimensional sphere that we're describing the overall energy level. In this case, this would be the 2s sublevel. Okay, and if we looked at the probabilistic distribution of where an electron can be found somewhere within the 2s sublevel, it actually has this kind of a distribution where you've got areas of dense probability separated by areas of very low probability of finding an electron there. These are kind of what we call nodes. This is low probability. And then we have these areas here where we have a higher probability. Okay, it's not just one normal distribution. It's actually quite complex. If we were to map it out this way, see here's our square of this of psi. So that's our orbital. And if we were to just plot the distribution, this x-axis, this is just distance from the nucleus. It's measured in picometers. So the nucleus is right here. And you can see that there's a little small distribution of where you might find a 2s electron very, very close to the nucleus. But then there's this node, and then further out, you get a larger probability of where you can find the electrons there. Now that's just for 2s. If you go to the next graph, you've got 2s probability overlaid with 2p. Now with 2p, you don't have that extra distribution. You just have the one distribution. I don't need to trace it over in blue. You can see it for yourself. If you go to the 3 principal energy level, you've got the 3 sublevels, the 3s, the 3p, and the 3d. And you can see those probabilistic distributions overlaid on each other. Okay? Now, the closer the electron can get to the nucleus, the more stable it will be. So even though in this distribution, let's look at the 3s's here. This 3s distribution, you got a little bit that's really, really close to the nucleus, even though most of the time it's found farther away from the nucleus. But if you look at the distribution, this is some part of the time, there's some probability that that electron at the 3s sublevel can get closer to the nucleus than any of the others, than the 3p or the 3d. You see that on this overlay? Right, if I trace, here's the 3p. Now at 3p, we do have 2 distributions, but still, the closest that the d, sorry, this is p. The closest that the p distribution gets to the nucleus isn't as close as the s. So there's some probability that an electron in the s sublevel gets closer to the nucleus than the p, so it's a little bit more stable. So s is more stable than p, and d is even a higher energy level because it's not quite as close to the nucleus. Right, here's the d distribution. All right, so that's all within a given principal energy level we always have this situation, etc. Here, I'll show you. This is as close as the D's will get. All right. So that's fine if you're all within a principal energy level. But now we're trying to describe why is it that 4s fills before 3D. So here I've taken the distribution of a 4s that's here in blue. It's dotted in blue, but I'll just overlay it here. 1, 2, 3. Now we've got 4 distributions. This is the 4s electron distribution. Yeah, most of the time it's way out here, far away from the nucleus. Once again, here's the nucleus. Here's the distance from the nucleus. Okay? But if we overlay that now with the 3D that I showed you up above, the 3D just has one distribution. Okay? This is its average distance as close as it can get to the nucleus. The 4s, based on solving the waveforms and then squaring them, the probability, there is a probability, it's small, but it's real, that a 4s electron can get closer to the nucleus than a 3D electron can. And if it can get closer to the nucleus, it's more stable. All right? So there's a little bit more insight. It was a little bit more in depth, but this is a little bit more insight. It explains why 4s fills before 3D. There's other explanations as well, right? But I want to just give you a little bit of insight. We're not getting more into quantum theory here, okay? This is one reason or one explanation. Because the 4s electron can get closer to the nucleus at least some of the time. So it gives us a more stable situation, so the energy level is slightly lower. Okay. Now it's a bit of a dual explanation here, because that explains why it's more stable. But notice that still, most of the time, the 4s electron is found further away from the nucleus. All right, so let me just highlight that here. Yet most of the probability is further from the nucleus. And that corresponds to another trend that I pointed out to you earlier, which is that in general, the higher energy levels that an electron's in, especially the principal energy level, is further from the nucleus. You saw that in the Bohr model of the atom. As you got to higher energy levels, principal energy levels, the electrons in general are farther from the nucleus, okay? So at higher energy levels, the electrons are further away from the nucleus. So we really have two explanations going on here. The distribution explains what I just wrote down, but it also explains why it's more stable. All right, so let's solidify our understanding here a little bit and show you the same arguments, but with a different kind of energy diagram. This is right out of your textbook. And we've got on the y-axis now we have increasing energy, okay? And now we've got these little orbital diagram boxes. And let me use this to highlight something else as well. If this is our 1s level here, okay, energy level, and then here's our 2s energy level, that's going to be, sorry, 2s and 2p. So here just n equals 2. N equals 1, n equals 2, n equals 3. We have the 3s, the 3p, and here's the 3ds up here. So we've got, this covers the 3s. The 4s are covering here. We're starting to get some overlap with 4. With 5, we're getting more overlap in 6 and 7. I don't have room to write all that in. But this shows you another trend that we also talked about with the Bohr model. As you get higher in energy level, the difference between energy levels gets smaller. So that's also shown on here, okay? So the higher the energy level, the smaller is the difference between energy levels. So I just want to orient you to what we're looking at here on the slide. Don't pay attention to this zigzag here yet. I'll talk about that in a minute. Let's just stay focused on the left-hand side, and let's just practice our filling in the electrons, following the Aufbau principle, so the order of filling. And then when it's appropriate, we'll emphasize Hund's rule as well, okay? So you should all know how to do this by now. We start with the lowest energy level, 1s, and there's room for 2 electrons, one is spin up and one is spin down. The next available energy level is at 2s, spin up, spin down. Then when we get to 2p, we're following Hund's rule. We're putting 1 in each of the degenerate orbitals with the spins all in the same direction before we go in and double fill them. All right, this is all reviewed. We did a lot of this at the beginning of lecture. Once 2p is full, the next available energy level is at 3s. So we put in 1 electron there. That would, if we stop there, we would have sodium. If we did 1 more, we'd have magnesium. If we go beyond that, let's follow Hund's rule again. It's looking exactly the same as what we did at the 2p level. All right, the trends are all the same. If we were to stop here, we would have what? What is this? This should be argon. And without counting them, you should get pretty clever with knowing how many electrons that is. Of course, you can always look at the periodic table and see that argon is atomic number 18, so you know that that's 18 electrons. That's also going to be where you're most stable, if we're going back to that idea of forming ions and being isoelectronic. All right, we now know from this recent discussion that the next electron for potassium is going into 4s. And that's shown conveniently for us here on this energy diagram. 4s is slightly lower in energy than 3d. Okay, but when we go beyond that, potassium, all right, then calcium, and then what's next? Strontium, all right, Sr. That electron is going to now go into the 3d sublevel. That's what's coming next. And we fill us in strontium, titanium, vanadium, chromium, manganese, iron, you can't see, cobalt, nickel, copper, zinc. All right. As we're filling in, now we're in the transition metals. Now we're in the D block. Here we are at the D sublevel. Okay. So as I fill these in, 1, 2, 3, 4, 5. If I stop here, what atom am I describing? What is it? Should be manganese, right? Because we're 5 in to the transition metals now, right? And now I followed Hund's rule. We had 5 degenerate orbitals. So I've got 1 electron in each of those degenerate orbitals, and they're all the same spin. And now I have to go and double fill them. 1, 2, 3, 4, 5. Now 3D is completely full. If I stopped here, what atom would I be describing? Zinc. But now that 3D is full, look what comes next. 4p is next. So now if I go in, I'm back in the P block. This aligns with our organization of the periodic table. So now we've got gallium and germanium and arsenic and selenium and bromine, and finally we get to krypton. But those are now going into the 4p block, and you can see those as they're mapped on the periodic table. If we go 1 beyond this now that next electron is going into 5s. So now we've got a new valence level. That's why I said earlier that your valence shell is full when the s and the p orbitals for that energy level are filled. Because what did we do here? We filled 3s, 3p, and then we went P was full. So then the next electron goes into 4s. But then after we filled 4s, we went back and filled in the rest of 3d, because we just understood now that 3d is slightly more energetic. All right, so it's going to fill in, but we're still at the valence level of 4. We haven't gotten to the next higher valence shell yet. We're still at n equals 4, even though we're filling in the 3ds. We're not done filling in 4. 4 isn't as stable as it can be until you've gone back and finished filling in the 4p orbitals. Once the 4p's are filled, then the next electron gets you to the next higher energy level. Okay, so it does get confusing when we have to go back and fill in like 3D and stuff like that. But you can see now why I said earlier that it's not completely full until the P is filled up. Once the 4P is done, okay, then we get to 5S, and you can see it gets more confusing as we go on, okay? The order of filling gets very confusing beyond this point. This zigzag here is the textbook's way for you to remember what the order of filling is. And it goes like this. You start with 1s, and then you go to 2s, and then from 2s, 2p's over here, and then you go over here, and over here, and then all over the place. Can you remember that? Is that a good study tool? Yeah. You can ignore that figure from the textbook, right? It's not very useful at all. Now, some of you who had chemistry more recently in another class might have seen this kind of setup where you say, okay, well, at n equals 1, I have the S sublevel. At n equals 2, I have a 2s and a 2p. At n equals 3, I have 3s, 3p, and 3d. At n equals 4, I have 4s, 4p, 4d, and 4f. And we can continue along this. And then you go through and you draw diagonal arrows through it, like this. And that shows you also the orbital filling diagram. You do 1s first, and then you fill in 2s, and then you do 2p, and then 3s, and then 3p, but then you hit 4s before you hit 3d, and then 4p, and so on and so forth. Did people learn it this way before? Yeah, some maybe. I don't even recommend you do it this way. All right. I've already shown you a really great way to think about this, where you don't have to remember any kind of fancy diagram that you have to set up and draw arrows through. You've got the periodic table, and you know how it's organized based on quantum theory. All you have to remember is that the S block is over here, the P block is over here. Now the D block is here, okay? Now you do have to remember one thing about the Ds. What's the first principal energy level where you get a D sublevel? It's at 3. You got to remember at n equals 1, there's one sublevel. That's S. At n equals 2, you've got 2 sublevels, S and P. At n equals 3, you have 3 sublevels, S, P, and D. So the first time you see a D sublevel is at n equals 3. And if you know that this is the D block here, then you have to know that these elements here in the first row of the D block, that's the 3D, even though it's at n equals 4. That's really the only thing you have to remember. But if you've studied your quantum theory, you'll already know that. Now you can just read along the periodic table. And you know when you're done filling in 3p, you're going to fill in 4s, and then you fill in 3d, and then you come back in and finish the 4p's, and that gets you then to 5s. And 5s, then after 5s, you know what's going to fill in first, 4d. Then you get to 5p, and you're done. When you get to 6s, now you got to come down and pick up transition, the inner transition, because now we jump down here. So what's the first principal energy level where you get to an F sublevel? 4. So these are going to be the 4Fs, and these are going to be the 5Fs, and so on and so forth. Okay, you've got the map of the periodic table to show you. All right, this is a good place to stop. Good practice today. We're going to finish this chapter material up with some more practice and a couple of new ideas on Friday's lecture.